Hey, what's up, guys? This is Chung here. So today's daily challenge problem, right? Number 1192, critical connections in a network. So this one is a very classic, a graph problem. Okay, so let's take a look at the description here. So they're like n servers numbered from n to 0 to n minus 1, right? Connected by undirected server to server connections, right? Basically, you're given like a connected graph, uh, connected undirected graph, right? And we need to find all the critical connections in this graph. So what does a critical connection means, right? So a critical connection is a connection that if removed will make some servers unreachable, right? Which means that there are like some uh, edges, right, in the graph. If you remove some of the edges, basically this server, but basically this graph will become uh, unconnected, right, for some parts. So for example, right, we have this one, so the answer is 1 3. And why is that? Because for this 1 2 0 1 2, right, we can remove any of those graphs, right? And after doing so, this 1 0 1 2, they are still connected. But if we remove this 1 and 3, right, if this one is gone, basically there's no way we can reach 3 from 0 1 2, or the other way, same thing. There's no way we can reach uh 0 1 2 from 3, right? Basically this is something like a bridge, right, between two components. And the constraint is pretty standard, right? 10 to the power of 5. Okay, so after reading the descriptions, some of you might have some already have some thoughts, right? So it's kind of obvious that is that we just need to find like a graph, right? Find a edge in the graph that serves like a bridge. But how can we do that, right? So let me try to give you some examples here. So what is a graph? Or what is a bridge in the graph? So let's say if we have some like edges here, right? This is another one, maybe this one. Okay, okay, right. So if I give you this example here, right? So what are the bridges? What are the critical connections here in this graph? So we have this one and 2, right? Because only these two edges are bridged, because all the others, we can always remove one of them. But after doing that, this the connectivity of this graph of these components that doesn't change, right? So now the problem becomes to what? Becomes to oh, and before doing that, so but how did we find these bridges, right? If you look at each of the components, right, we can clearly see that a bridge or a critical connection or is not does not belong to a circle, right? Because all these kind of components, they're all they're all part of the circle, right? Even for this one. So which means that if an edge is not part of a circle, then it is a connection. It's a critical connection. And for this kind of components, for each of components, this one is not like a strongly connected component, right? So it's a little bit different as strongly connected components. In this case, so strongly connected components means that any pair and each pair of these components will have like an edge, right? But this one is not. This one is a strongly as SCC. This one is not. This one is not either. So this in our case, all we care is that if this edge or if this node is part of if this edge is part of the a graph. Oh, sorry, a circle. So now the problem is that how can we find edges, right? Belongs to part of a circle. You know, mm, we all know that to detect if a circle exists in a graph, we can simply use a DFS, right? I mean, so let's say for example, we have this kind of node here. Now this node, right, and then like this one, right? Let's say we have this kind of a 0. Never mind. So we can simply use DFS, right, to check if a circle exists in the graph, right? We simply uh, start anywhere, right? We can start from anywhere, and then we do a DFS, and every time when we see a node, that has not been visited, right? We mark that node to be visited, So when we see the moment we see a node, the moment we see a neighbor which has been visited before, then we know that okay, we have seen like a circle, right? Basically, if we mark, so if we see this one, it's not visited, and then not visited, not, not, and not, right? But when we reach at this node here, we have seen okay, one of the neighbors, they have already been visited, right? I mean, of course, we'll not consider the parents, right? So when we find the neighbors, we'll simply ignore parents. So basically, when we reach this one, this node here, we're not looking at parents. So we see, okay, the neighbor is this one, but this one has already been visited, which means we have find like a circle, right? Then it means that, okay, so this one, this node, this edge is part of the circle. We can simply remove that, right? So let's say we have a B, C, D, E, and F, right? So which means that the edge C and F, we know okay. So certainly it's apparently it's like part of the circle. We can simply we know that we can simply remove it from the edge set. So what I'm trying to do here is that if we can remove all the edges that belongs to a circle, so what's left in that set will be our answer, right? So this is clear, right? But the question is that how can we remove the edges? The CNF it's already removed, but how can we remove the edges for all the other edges like CD, DE, and EF, right? So how CD, DE, and EF? This one we already know because we detect a circle here, right? That's when we remove this edge. But how about this three? Because when we are traversing this kind of three nodes here, we don't know if there's a circle at this time. So how can we do it, right? So in order to do it, we have to use something like a labels, or you can call it a rank. Basically instead of, like I said, to detect a circle, we mark this node to be visited. So we can mark it instead of simply mark it, we can simply give like a label or a rank to each of the node. Basically, the sequence we visited this node. So for example, if we visited this node, so I would give this one a label 0, right? And then the next one will be 1, and this one will be 2, right? And so on and so forth. And the next one will be 3, 4, and 5, right? So Oh, by the way, so this algorithm, it's called Tarjan algorithm because this algorithm was created by a guy called, I think, Robert Tarjan in 1970s, if I'm not mistaken. But okay, regardless, So basically, we have like a label here, Since we have already visited 2 here, Now, when we are at 3 or 4 or even 2, right? Because 2 we also need to know if this 2 is like part of uh the circle, if in the DFS, right? So we always use DFS. So if in the DFS, if we return the minimum labels for each of the node here, so which means that when we are at 3 here, we call DFS of 4, right? And then in 4 we call DFS of 5, and in 5 we call DFS of 2, right? But since 2 has already been visited, we simply return uh, that label, right? And in each of the node, we always return the minimum label that we can get from 5. So which means that when we're at 3, 4, and 5, we'll always get 2, right? And then we can simply use that returned like minimal label to check. Basically, as you guys can see, if the current label value is either greater, if the current label is either equal greater than the return one, right? We can call it a recursive, right? A recursive label here, then we know, okay, so this node, right, or this edge is part of the circle, right? So it makes sense, right? Because if we're at like 1 here, so we are at 1, right? So what's going to be the the recursive of 1 here? Because at 1 will recurse with 2, right? So the two returns what? So the 2 returns 3, 4, 5, and then back to 2, right? So the 2 will return 2. That's why for 1 and 2 is not a part of the circle. But if we have like another edge, let's say from 5 to 1, okay, so now 1 is part of the circle. And why is that? Because so let's go over this logic one more time. So from 0 to 1, from 0 we recurse to 1, right? From 1 now we recurse to 2. Same thing, right? Same thing for 2, 3, 4, and 5. Okay, so keep in mind that so now 5, uh, besides the parent, it has 2 neighbors, right? It has 1 and 2, and where both of them have already been visited before. So when we return at 5, we return the minimum between those two, which is 1, right? That's why when we are at 1 here, so when this like the recursive finish, this one got return to here. Now 1 is also part of the well, basically now 1 equals to 1. So that's why we can tell. So now this 1 is part of the also part of the cursor, right? Yep. So that's the basic idea. So it's basically 3 steps, right? A few steps. So we start from a DFS traversal, and then second, when we mark the visited nodes, we add like a label for each of the unvisited label, and then in the end, right, and then we will also compare, right? We also compare if the if the current one is greater than the recursive label. If it is, and then we know, okay, we can remove the current. Then we know the current node or the current edge between the the child and the parent node is part of the circle. We can safely remove it, right? And then in the end, we return the minimum, like label among all those kind of recursive labels. Yep. So let's then start coding. Let me see. So first thing first, we want to create like a graph, right? So the graph is going to be a default of dictionary, dictionary of list, right? And this is all standard. We have for u and v, right, in connections. We have graph dot u dot append v, right, and then we have graph v dot append u, right? And then, like I said, I'm going to need like a label, right, for each of the node. So at the beginning, I'll assign the label to -1, I guess, or you can use 0. It doesn't really matter. I think for me, I use 0 because maybe the first one I use will be 0 or 1. But anyway, I initiate everything with -1. And yeah, and for the answer, since this list is kind of like is a list, when we remove from it, it will be a O of n time complexity. That's why, to make the remove faster, I will create a set. I'll convert this connection to a set, right? So that's why, I'll just use I'll put everything into an answer set, right? And when I'll just use the same for loop here. I'll just add this one to the answer. But since the sequence, so since these connections could be either 0, 1 or 1, 0, because when we visit this, when we do the DFS later on, the sequence is not guaranteed, right? So 2 could be the parent, or 1 could be the parent. So either one is possible. That's why when we initiate the answers, we can define like a criterion, which means that we always put the smaller node before the greater one, right? So we can simply do a minimum of u and v, and then the max of u and v. So just a little trick, right? To remove some of hassle here. Okay, and then the DFS, right? So for DFS, first one is the current node, and I use like the parent. I also pass in the parent just to help us to determine if the neighbor is the parent, right? Or you can use some other ones, but I just say prefer to also pass another, like the additional parameter for the parent. And then the last one is the pre-label. So basically, it's pre-label means that it's the biggest label we have been assigned so far, right? Cool. So the exit condition, which means if the current one has already been assigned to a label, we simply return that label, right? Which means that if the labels dot u, right, is equal greater than 0, right, then we return it. We simply return that label because it means that we have already visited that node labels. Okay. Otherwise, we assign the label for the current node, right? It's going to be a pre-label plus 1, right? Current node. Okay, so now the next one is that we loop through all the neighbors, right? So for v in the graph, right? Graph u here, and we also gonna maintain like a label, right? The minimum label of the current node, which means that what is the minimum label we can see from the current node. right? Which is the system at the beginning. It's system.max, right? So for here, first we check if the v is equal to the parent, right? We simply continue. It means that if the neighbor is the parent, we simply ignore it, right? Because we don't want to revisit the parent or go back to the parent. Otherwise, I have this kind of recursive label, right? I mean, from the DFS. From the DFS of what? So now the current one becomes to V and the parent becomes to the current. The current one becomes to the neighbor and the parent becomes to the current one, right? And then we also pass in the labels, right, of U. That's going to be the last label we have assigned. And like I said, so if the labels dot U, if the current one, right, is either equal or greater than the recursive labels, right, then it means that, both U and V is part of the the circle, right? Which means that we can remove, which means the edge U and V is also part of the circle, and we can remove it. Once remove from, we can just copy and paste this part, since we're gonna use the same logic here, right? So this one means that U and V, right, are both part of a circle. And then keep in mind that every time we have like a recursive, we're gonna update this minimum label, right? The minimum label of the recursive, right? And then in the end, we return the minimum label, right? So this one is like necessary because remember, so if you remember this one, so we have 0, 1, 2, 3, 4, and 5, right? So if 5 has another like edge to 1 here, when we are at 5, right? So 5 have two neighbors, have two v's, right? One is 1, the other one is 2. But here, we want to return this one. We want to return 1 instead of 2, right? That's why that's why when we at 1 here, when we add 1 here, 1 recurses to 2 and all the way to 5, and then in the end it will return 1, right? And when we are at 1 here, if we go back, right? So 1 will pointing to 2 in this case, right? Because we are using the DFS, even so even though 1 has 2 neighbors, which one is 2, the other one is 5, but since we're using DFS, basically it will always follow one path to the end, which means that it's gonna follow 2. So 2 also have 5 to 3, but assuming we'll always go to 3 first, and then 4 and 5, right? And when we're reaching 5 here, so 5 will get we'll see, okay, 1 is already visited, right? And 2 is already visited. That's why 5 will return 1. And then when it backs to 1 here, so here u is 1, right? And then this label is 1. So the recursive label for the 2, for the recursive, this one is also 1. That's why we're gonna use the label equal greater than 1, so that we can remove this edge 1 and 2 from the answer set, right? That's why that's how we can remove 1, the edge 1 and 2. Yeah, and when we reach at 1, 5, I think that will just simply be ignored, because so when the u is 1, right? So we have 1, we have 2 and 5. So 2 has already been set, right? Has been processed, and then for 5, when we are reaching 5, but the 5 has already been visited, right? So which means that for the branch of 5, when we are at a 1 node here, it will simply be it will simply return label 5 in that case, right? And yeah, but this one will not be affected because so in that case the recursive label will be 5, but 5 is greater than 1, right? That's why the minimum label for the node 1 is still 1. Okay. Um, yeah, I think that's it. And if there's no circle at all, right? So in that case, it's just a uh, one single like line here. In that case, if we start from here, the starting point is max size. So for the neighbors, so this minimum label will be what? Will be there always be like I guess the system max, right? Which is fine, I think, because in that case we simply don't um, let me see here. Yeah, because in that case, the minimum labels, if in this case they're all like system max, because we'll never uh, because this recursive label, right? I mean, it will always be the system max in this case. And but since we're comparing this label, the current label with this recursive label, the current one we start from 0, right? Will never be greater than the system max, right? That's why we can either use if the system max size is fine. Okay. Okay. Sorry. So sorry about the side track here. So let's finish this code here. So after implementing DFS, the last thing is just simply do a DFS. We start from 0, right, and the parent from node 0 -1, and then 0. So this one, we can start from any node from 0 to n-1 will work. I'm just happen to pick the first one, and yeah, and the labels are starting from 0. Actually, I start from 1 because uh, because the first one will be the pre-label plus 1. So that's why the label starts from 1, but it doesn't really matter, right? And now I simply return the answer. So that's it, right? So if I run the code, accept it, right, and submit. All right, cool. I mean, yeah, so that's it, right? I mean, the time complexity, right? I mean, so this is like standard DFS search on the graph, right? So which makes it the time complexity is the V plus E, right? Where V is the number of the nodes and the E is the number of edges, right? And the space complexity is O of E, right? Because we are creating actually we have a graph here, so the graph is like is total number of the edges, right? That's going to be the total time complexity. And yeah, because in this case, edges is either equal or greater than V. Not necessarily, because in this case, edge is equal to v minus 1 if it's a tree, if it's a spinning tree, right? But if it's like a completely if it's like strongly connected graph, so this edge is greater than v. But v and e and v, e will be will have this greater like scale, right, of v. That's why I use e to represent the space complexity, right? And yeah, and so just to recap real quick, right? So this problem actually it's essentially asking you to find the edges, right? Or to find the edge if this edge it belongs to a circle, right? So the way we're checking that is that we mark each visited, we assign each visited node a label, right? And then at each of the recursive call here, we're getting the the recursive label, right, from the recursive call, and we compare that if the current label is either equal or greater than the recursive label. If it is, then we know it's part of the circle, and then we can simply remove the edge. Yep. So that's the core concept here. Yep. I'll just stop here. Thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.